Welcome back. Now, we've seen already intermodulation products and gain compression, and both are effects that limit the dynamic range of the receiver. They set up the upper limit of the dynamic range of the receiver. Now I want you to see two things. First, that IP3 and the 1 dB compression point are related for the case of third-order nonlinearities, and also that we can derive some cascading equations for both of them. Let's see. If you recall, in the previous sections, we've defined the ratio R, which is the ratio of the desired signal to the intermodulation products, right? Now, by using the formulation of nonlinearities that I've explained before, these powers can be written as shown in this equation, and this equation can be simplified as shown here, right? Now, the input intermodulation point occurs, if we set the input power equal to the input intermodulation point, what we will have is that this parameter R will be equal to 1, and therefore we can take this equation, make it equal to 1, and solve for the value of 1/2 of, and see for what value of this parameter 1/2 of A1 squared we have R equal 1. And this gives us IP3, right? The third order intercept referred to the input, which is 2/3 of K1 divided by K3. So the third order intercept only depends on these nonlinear coefficients K1 and K3. On the other hand, recall that in previous sections of this lecture, we found that P1 dB followed this equation. So both parameters are very closely related. P1 dB equals IIP3 multiplied by this factor, which turns out to be 0.11. If we convert this to a logarithmic scale, we will see that the 1 dB compression point equals to the third order intercept minus 9.6 dB, right? Now, in practice, however, these two parameters, P1 dB and IP3, are measured independently because one cannot be sure that the nonlinearities will be pure third-order nonlinearities. They can be other terms, right? In any case, it always happens that the 1 dB compression point it's lower than the third order intercept referred to the input. Another issue is what happens when we have two nonlinear devices in cascade, right? And again, we assume that both have third order nonlinearities. So in this case, Y would depend on X as we have described before, and Z depends on Y with the same type of dependence, right? In this case, we can develop a polynomial dependence of Z dependent on X, and we find that this dependence will have a term in Q3 and a term Q1, right? Which would be the nonlinear coefficients of the joint dependence of these two elements in cascade. Accordingly, this coefficient Q1 will be the product of P1, K1, these two elements in here, and Q3 will have this dependence, right? Now, using the equation for IP3 that we have developed before, IP3 would be 2/3 of Q1 divided by Q3, right? And then the reciprocal of IQ3 can be put in this equation, which is the reciprocal of 2/3 of K1 divided by K3, and the reciprocal of 2/3 of P3 divided by P1 multiplied by K1 squared, right? And if you look at that, this is the third order intercept of the first element, and this is the third order intercept of the second element, and this is the gain of the first element. Or in other words, now if you divide all this by the product of G1 and G2, you convert this third order intercept to the output. So the output third order intercept of the chain would be equal to the output third order intercept of the first element multiplied by the gain of the second element, and the output third order intercept of the second element. And this equation can be easily generalized if we have more than two elements, and in this case, in this first term we would have the product of all the gains. In the second term we will have the product of all the gains except for, in this element, in this point we have the product of all the gains except for the first one. In this second term we would have the product of all the elements except the first and second one, and so on. So in this way we can generalize this equation, which in principle applies for only two elements in cascade. And again, since the 1 dB compression point and the third order intercept are proportional, one can very easily show that the 1 dB compression scale follows the same type of dependence, right? And again, this dependence is useful to foresee or to predict both the third order intercept and 1 dB compression point of a chain. But again, recall that in any case, this nonlinear model for all these elements has very the assumptions that are made are very restricting, and therefore these equations have to be taken with care, because in practice there are many elements that may make them not directly applicable. For example, mismatch and other things. But they give a rule of thumb of what would be the overall third order intercept and the overall 1 dB compression point for a receiver chain.